you're just going to... Sines, reciprocal is cosecant, CSC. This will be 1 over y or 1 over sine. Either one's perfectly fine. And tangent, of course, is cotangent, which is x over y or cosine over sine. Cosine over sine. Now these x's and y's, you have to remember, are on a unit circle. They cannot just be any old place. It doesn't make any sense unless it's on a unit circle. Unless you can have x squared plus y squared equaling 1, don't even try using those coordinates. Because it has to be on a unit circle.
I know.
Alright, I thought you said y.
No, I said what?
Oh, whoa.
Like I was confused, I forget what y squared.
I was confused. Alright, so that defines them at least on a unit circle. Okay. What I want to do is get it off a unit circle because unit circles are only good for what I consider the 4 corners. 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Other than that, I don't have you memorize all the possible coordinates around this thing because they get kind of, well, confusing. So what I'm going to do is change our definition a little bit. I don't know, I need to know something. I don't know if they split this off into a separate section. Section 3. Yeah, this is 4.3. I don't spend a lot of time on the unit circle.
Are you done with 4.2?
4.2, yeah. I don't spend a lot of time on it. They get into a little bit more detail. They want you to memorize the whole unit circle picture, but I don't see any point in that. So 4.3, we're going to change things into the more applicable version, which is generally the one you're going to use anyways. Very few people, when they get up to calculus, go back to a unit circle. Most of it's based on triangles.
Sohcahtoa, is that what we're getting into?
We're getting there. So to do that, though, we have to carry our definition of the unit circle into another realm. In other words, circles that are of any radius whatsoever. So I have to draw a few pictures here. Where are all my markers? Picture number 1, our general unit circle. Let's make it kind of small here. So this is the coordinate 1, 0. That pretty much defines that it's a unit circle because the radius is 1. Then I'm going to include another circle. Bigger. It doesn't have to be bigger, but I'm going to make it bigger. Let's put it out here. That's not bad. And let's call this R0. Where R can be, well, anything, any length. And I'm going to throw in an angle in here, just a random one. I'll put it in the first quadrant because that's where it's going to work the best. So we'll start here at the origin, we'll cut out over here to this point, and it runs into the unit circle there. Now I know the coordinates of the first blue point here, this one here. I know this is cosine, oh, give this an angle, call it theta. Cosine of theta, sine of theta. What I don't know is the coordinates of that point out there. So I need to figure out a few things. So first things first. If I draw a little triangle here, I'm going to label it off to the side. Here's the radius. The radius is 1. And this angle is theta. So this is the small unit circle triangle that I've defined. Drop it right down from the cosine theta, sine theta, straight down, and then across on the x-axis. If this is cosine theta, sine theta up here, and this point down here is the origin, 0, 0, what's the length of the base of this triangle?
Wait, hold on. What?
If this is the origin, 0, 0, and this point up here is cosine theta, sine theta, what is the length of the base of this triangle?
Sohcahtoa.
Don't be, I don't even know what that is yet.
I don't either.
1.
How far is it from here to here?
1.
Oh, I'm really worried now. If I have these 2 points.
Oh wait, no. It's 2.
Hold on. If
X
that's
squared
0, 0.
equals 1 squared.
Stop. And this is the coordinate
Square
3,
one.
5. How far is it along the base of this triangle?
1 over the square root of 2.
No.
What?
3. How high is it? 5.
Okay, but that one over there.
What's the length of the bottom here?
Cosine.
Cosine of theta. What's the height?
Sine of theta.
Sine of theta. It's the x coordinate and y coordinate because you're starting at 0, 0. It's cosine theta to the right and sine theta up. Stop shaking your head. That's what it is. All right, I can make a bigger triangle over here. And what I don't know is the lengths of those two sides, so I'm interested. When I set it up, I'm going to set it up like this. Here's the big triangle, and here's the little triangle that the unit circle is defining. So I don't know the lengths of this side and the length of that side. That's what I need to find. But this one here is cosine, and this one is sine, and this little radius from here to here is 1. What's the radius of the whole thing?
1 plus whatever that is.
What's the radius of the big triangle?
The radius of the big circle. R.
R. So this is R. What's true about the little baby triangle and the big triangle?
There are proportional.
Proportional, because they are right triangles are inside of one another are proportional because they are begins with an S.
Symmetrical.
Similar.
Similar. They are similar triangles.
I was scared.
All right, so let's call this side. What should we call it? Let's call it A, and let's call this side B. If these triangles are in proportion to one another, then let's set up some nice ones, like sine over 1, sine of theta over 1 is equal to B over R. B over R.
Is that a C or what is that?
This one?
Yeah.
Yeah, that's a little C for cosine. I just didn't want to write it all out. Cosine theta. All right, another one we have that's nice and easy is cosine over 1. This cosine over this 1. So cosine of theta over 1 is equal to A over R if they're in proportion. So capital A over little r. And while we're at it, there's another nice one. It actually comes from over here. Y over x, which is sine over cosine. So if I do sine over cosine, sine of theta over cosine of theta, also known as tangent of theta, this is going to equal, careful,
B over A.
sine over cosine, b over a. All right. So we have these nice little ratios. So it kind of works out this way. The sine of theta from our original little unit circle is a ratio of the sides of the bigger triangle, which is b over r. Now b is over here, theta is over here, so to give it a name, we're going to call this side opposite. It is totally opposite the angle. It's not touching the angle, it doesn't form the angle, it's completely opposite the angle. So this is going to be opposite, and the radius of this triangle has a special name already,
Hypotenuse.
hypotenuse. So we're going to define sine of theta to be the opposite over hypotenuse.
Wait, so B is now opposite, right?
Opposite the angle. It does not form the sides of the angle. The angle is formed by the hypotenuse and this leg down here. So the side is, this side that does not touch the angle is called opposite. Okay? Now cosine of theta is equal to A over R, but A is this side, and this is a leg, but that it's touching the angle, so we're going to call that adjacent. That one actually works out rather well. It's adjacent, it's touching. Adjacent means you're touching the side. So it's adjacent, and then we already talked that R is hypotenuse. Now sine over cosine, of course, is tangent, and B is opposite, and A is adjacent. So this is opposite over adjacent. And this is where you get sohcahtoa. 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 I could never remember sohcahtoa.
Someone I know that he took it on acid.
Yeah, that's a funny one.
I could never remember that one.
Some old hippie caught another hippie tripping on acid.
I always remembered it since I was a kid.
So either one way or the other,
Wait.
another hippie tripping on acid.
I could never remember that one. That's
Yeah.
so easy.
Sadly,
I
I
know. You
think
see it all the time. I know, right?
Tripping on acid. Tripping on acid. There's something going around in the 80s. So you either remember sohcahtoa.
I don't like it because
This is the Indian name.
Sohcahtoa.
The problem I had with sohcahtoa is I'm a horrible speller.
Sohcahtoa.
So I would get the O's and the A's kind of in the wrong place. So the other one, some old hippie
That one's just too long for me to write out too.
caught another hippie.
Did you
Is
say
it
hippie?
HYPPI?
Hippie is with an I.
Is it
It's
HI?
HI.
PPIE,
That's just pretty expensive.
tripping, and this is not a very good thing to be doing.
Put on acid.
Acid.
Yes, it is.
No, it's
No,
not.
it's not.
Acid is PCP. PCP is very dangerous. But it stuck in my mind, and I could remember which one went to which. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So now you can do something like this. For example,
That's because that's what it's supposed to be.
now obviously 3, 7 is not on a unit circle because 3 squared is 9, 7 squared is 49, and 9 and 49 is 58. And 58's square root is definitely not equal to 1. So if you tell me on this problem that cosine of theta is equal to 3, something is wrong. Big wrong. So if you want, you could draw a little picture. 3, 7 is someplace over here. And you get this little triangle. Nice little right triangle. How long is the base of this triangle? Let's argue over this one. 3. How high is this thing? 7. Does it matter how badly the picture is drawn? No, I drew it purposely horribly.
That is awful.
I know, isn't that horrible of me? But it doesn't matter. As long as you get your sides labeled correctly and in the right place, you're perfectly safe. Now, if we're going to do trig on this, this is the angle we're talking about. This angle here opening up the initial side and the terminating side. To find the trig of this, you need the hypotenuse, because each one of these, well, 2 of them at least have a hypotenuse in it. The hippies. Now, if you, to find the hypotenuse, you have to do, c squared equals a squared plus b squared, better known as Pythagorean theorem, backwards. Why? Because c is much more important than a and b. C happens to be, well, it's the hypotenuse, so leave it alone. So this is c squared equals a squared plus b squared, which is 9. I already talked about this. 49.
Yeah, that's why we
So
do
c
it.
squared equals,
The square root of
well, this is 58, and this becomes c equals the square root of 58. Does it break down?
No. Well,
2 and 19? No, 29?
yeah. It's
Or-
2 and 29.
Is it?
It's 2 and 20. Yeah.
2 and
Yeah.
29, yeah. So that doesn't break down. All right. So once you have this side as the square root of 58, 58, what is the sine of this angle equal to?
7 over square 58.
7 over the square root of 58. Opposite of that angle over the square root of 58, which is the hypotenuse. What is the cosine of this angle?
3.
3 over the square root of 58. Perfectly fine. And tangent of this angle?
7 over
7.
7 over 3. Now what's really cool is if this was the equation of a line, what would be the equation of this line that forms this angle?
3. What?
What would be the equation of this line going through 3, 7 and 0, 0? Equation of a line? What's the slope? 7 thirds. And it's going through the origin, so the equation of this line is y equals 7 thirds of x. And you'll notice that
Cool?
tangent is also 7 thirds.
Yeah, you told us that earlier.
So the tangent of an angle is the same thing as the slope of a line.
Can you use this for any right triangle?
Any right triangle you have, trig works on it automatically. Now when it turns into not a right triangle things, that's chapter 6.
Oh.
We'll get to that.
No.
But sine and cosine, you can write it like that.
The functions themselves do not change in
What
other
about-
triangles, just the formulas will change.
Do we not have to find?
But the idea of opposite over adjacent, opposite over hypotenuse, and adjacent over hypotenuse never change.
Do we not have to find the secant, cosecant, and cotangent?
Yeah, I'm getting there. I just wanted to get rid of this mess first. So, we're going to do it in the order you suggested. Secant first. So what's the secant of theta?
Square root of 58 over 7.
And I would have to say no.
What?
Square root of 58 over
Oh.
3. You have to be really careful with secant. You never do SS. It's always SCCS. The letters will always be
Then
opposite.
why is secant beside sine?
Because she told me to say secant. I wrote
What is
secant.
secant?
I just wrote it. It doesn't matter. I couldn't ask them out of order. So let's do cosecant next. Which one is cosecant related to?
Sine.
It's related to sine, so this is square root of 58 over 7. And then the easy one, of course, is cotangent of theta,
Which is 3 over 7.
which is 3 over 7. Ta-da! So you just got to be really careful with that secant and cosecant. You always go opposite letters. It's never going to be exactly the same. So far, so good?
Is cotangent and tangent always opposite?
What's that? Cotangent and tangent, they're always reciprocals of each other, if that's what you're asking. Yeah. Don't say opposite, because that means signs. Alright, did that. Oop. Which one first? Let's do this one first. Cofunctions. There is a reason why there is a sine function and a cosine function. There is a reason that you have a secant function and a cosecant function, and a tangent function and a cotangent function. There's a relationship between all of those sets. And the relationship works out this way. Remember all your Greek letters I asked you to memorize?
No.
Oh well. This one is alpha. This one is beta.
You write your alpha.
It looks like a fish. It's supposed to look like a fish. Let's label the sides. Let's call this side A. Notice A is opposite of
The fish.
alpha, and beta up here, this side's going to be
B.
B, and of course the hypotenuse we're just going to call it C. This is what's called a general picture of a right triangle. So if I ask you for the sine of beta, what's it equal to?
B
Sine of-
over C.
B over C.
Yeah.
You have to look at the angle you're asked about, and opposite of it would be B, and the hypotenuse, of course, is C. So you get B over C. So orientation is really important. These triangles can be rotated any which way you can imagine, and you always have to recognize what's opposite, what's adjacent, what's hypotenuse. All right, what's the cosine of alpha equal to?
B or C.
B over C. So there's a relationship between these two functions evaluated at their respective angles because they're coming up with the same ratio, B over C. So what's the relationship between alpha and beta?
They're sine and cosine.
Great, no.
They're in the 2 angles.
They're what?
I don't know.
I think you said it.
I was about to say opposite.
No, don't want to say opposite.
They're the 2.
Begins with a C.
Congruent.
No, they're definitely not congruent unless this is an isosceles right triangle. Supplementary?
Complementary.
Complementary, which means
They add up to 90.
they add up to 90. This already has 90 degrees out of 180 degrees a triangle has, so this has to be, the sum of these two must be.
Oh, duh.
I was going to give you the definition.
Now, remember, pi over 2 is the same thing as
90 degrees.
90 degrees, but I'm trying to get you used to radian measure, because that's where calculus always goes, radian measure. So, if alpha plus beta is equal to pi over 2, then what's alpha equal to? By itself.
2
Pi over 2 minus beta. So what this gives us is that if I have the sine of beta, this is the same thing as cosine of pi over 2 minus beta.
Hold up. What?
We already said that cosine of beta is equal to b over c, and the cosine of alpha is b over c, so these two are equal to each other. Cosine of beta is equal to cosine of alpha. But I just said alpha was equal to pi over 2 minus, so I just substituted it in.
How do you know whether to use cosine or sine?
It doesn't matter. If I wrote cosine of alpha here, this would equal sine of pi over 2 minus alpha.
Why can't it be cosine pi over 2 minus beta?
Okay.
Oh, I get it.
So if I did
If this started with alpha on this side, it would have alpha on this side. If it started with beta on this side, it would end in beta on this side. It's just whatever the angle is over here, this one is pi over 2 minus that angle.
So it can't be cosine of alpha equals cosine of pi over 2 minus.
No, it's cosine to sine or sine to cosine.
Okay.
Yeah.
So it's basically like cosine of alpha equals sine of beta or whatever.
Yes. It's the same idea.
Why
So-
can't, for doing the top part, why can't you use tangent or something?
Tangent you can. You could say tangent of alpha, but this would equal cotangent of pi over 2 minus alpha. It has to go with their respective cofunction. So tangent goes with cotangent, sine goes with cosine, and secant goes with cosine. So if I asked you, the sine of 20 degrees is equal to cosine of what angle, you should be able to tell me.
It would be 7.
It would be 7. So the sine of 20 degrees is the same thing as cosine of 70 degrees. The cool thing about these functions is they're interchangeable. You can always replace one with another. And that makes things very, confusing, to say the least.
So would sine of alpha equal cosine of beta?
Yes. Okay. As long as you switch the functions, we're okay.
I just want to make sure.
Yeah, it doesn't matter what angle you start with. They're related.
Or what? Like,
All right, what's the other one? Oh, my favorite topic. More stuff to memorize. Because I do not teach all the coordinates on the unit circle, I do everything a different way. My way is always right triangle trigonometry, except for the quarters of that unit circle, 1, 0, 0, 1, and so forth. So if I'm going to not memorize the unit circle, I have to come up with another way of calculating these things. So I come up with, of course, the special triangles. Now you might know these.
Where did they track the crown?
If you start off with
Oh, I remember these.
not an isosceles triangle, an equilateral triangle, what is the measure of each one of the angles?
60.
60 degrees, right? So guaranteed, this angle here is 60 degrees. All right, geometry time. If I take an equilateral triangle and I drop an altitude, what does that altitude do in an equilateral or actually isosceles triangle?
It makes it a right triangle, but it splits the top angle into half.
It cuts the angle in half up top, so this becomes
30.
30. And what's it do to the bottom?
90.
No.
30, 60,
That's the
90.
base.
Oh, because
It cuts the base in half. So if the lengths of the sides were 2 each, what's the length of this little side here?
1.
1. So if I separate this out and kind of draw it flatter this way, where there's the 90 degrees, this is the 30 degrees, and this is the 60 degrees, then the hypotenuse is 2. The angle, the smallest angle has the smallest side, so opposite of 30 is 1. And opposite of 60 is that other side.
Oh, I know that.
What is it?
Isn't it the square root of 30?
Square root of 3. You could do the Pythagorean theorem on it. It would be 4 minus 1 and then the square root of it. So this side becomes,
Well, why is it, how'd you get 1?
oh, when you drop this altitude, it cuts this base into halves.
Oh,
And the length of it is 2, so that'd be 1, that'd be 1. And to get the square root of 3, you just do Pythagorean theorem, and that's pretty easy to do. So from this picture, you can say, well, what's the sine of 30 degrees? Just by looking at the picture. Yeah.
It's going to be
1 over 2.
1 over 2. Opposite of 30 is 1. Hypotenuse is 2, so you get 1 half.
oh.
Much easier than memorizing points. What is the cosine of 30?
Square root of 3.
Square root of 3.
Square root of 3 over 2. Adjacent over hypotenuse. Tangent of 30. Well, we're sticking on 30 for a little bit.
The tangent is going to be.
1 over square root of 3.
Opposite over adjacent, which is 1 over square root of 3. And then, of course, you can find secant, cosecant, and cotangent. Okay, so that's one of the special triangles. The other one comes from a square. And the lengths of the side of the square are 1. Each side is 1. We're going to cut it with a diagonal. What does a diagonal do in a square that is different than a rectangle?
It makes it isosceles.
Well, it makes an isosceles triangle. What's it do to the angles?
It cuts them in half.
Cuts them in half. It only works in a square. It does not work in a rectangle. So if this was a 90 degree to begin with, this is now down to 45 degrees. And you get this triangle.
25, 45.
1, 1, and the third side is?
The square root of 2.
Square root of 2. It's a squared plus b squared, which would be 1 plus 1, equals c squared, and then you have to square root both sides. So this is 45 degrees, also known as a 45, 45, 90. This one's obviously 30, 60, 90. And we can do things like, what's the sine of 45 degrees?
1 over the square root of 2.
1 over square root of 2, also known as square root of 2 over 2. When you rationalize the denominator, multiply top and bottom by square root of 2. And then cosine of 45 is boring, because by the cofunction thing, it would be 90 minus 45, which is back to
The square root of 2
45.
over 2.
Yeah, it's a square root of 2 over 2. There are cases where you want to leave it as 1 over square root of 2.
On a
Especially if you're going to be looking for like secant and cosecant. You can just flip it.
On a test, if we keep it in one.
Either one. I can care less.
Okay.
I can care less.
How'd you get the square root of
You multiply top and bottom by square root of 2. And then tangent of 45, the most interesting one.
1 over 1.
Which is better known as
1.
1. This is how you test your calculator to see what mode you're in. You type in tangent of 45 and your answer comes up to be 1, you're in degree mode. You type in tangent of 45 and you get something other than 1, you're in radian mode.
Do you want us to be in degree or radian?
Depends on which problem we're on.
Okay, what do you
Some are in degrees, some are in radians. So sometimes we're going to be going back and forth. Mostly degrees with so far. Mostly.
1.619.
Oh, when it's radians?
Yeah, I guess I'm in radian.
Yeah. Because if it's not 1, you're definitely in radians. If it is 1, you're definitely in degrees. All right, so you have these two pictures now. So you have to memorize. I'm going to tell you exactly what you need for the test. That unit circle picture I had on the board, these two triangles, and some old hippie or sohcahtoa, one of the two. You have to know those inside out, upside down, and I won't give them to you on the test. All right, so that's
Wait, I
special.
have to know someone who be tripping caught another. Can I just use sohcahtoa?
You need to know that by heart.
I know sohcahtoa by heart. I
That's
didn't
fine.
know someone
Sohcahtoa, some old hippie, I don't care which one. I don't care. As long as you know that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent.
Yeah.
Did I cover anything?
You done?
Oh, I haven't talked about calculators. I hate calculators.
I love calculators. They're pretty ingenious.
Yeah, they do everything in unit circle.
How do people use the old calculator?
Without a calculator? Yeah.
Wait, what? How do they do that?
Trigonometry without a calculator is very tricky. You have to have tables. Tables.
The very first
Yep,
calculator.
alright. Applications.
You mean an abacus?
To find trig without a calculator is very tricky. One way is to use that formula on the board over there.
I'm good. I'm really good. I'm totally fine.
But that's how your calculator does it, those two sine and cosine
Well, my
formulas.
calculator is pretty smart. What about tangent?
Well, you just do sine over cosine. And then all the other ones pop out of that. Alright, applications. For instance, you have a lake. You have a lake. Lake. And you're here,
That's an awful looking lake.
and there's this tree over here. Right? And the problem is you want to know how far it is across the lake, but you don't want to canoe over and drag a rope behind you because that's not a very accurate measurement because the rope is going to, well, it's going to sink under the water and cause a little bit more length. So what you're going to do is you're going to look at the tree from here, and you're going to walk a certain distance away at right angles. So you have to walk along the shore of the lake at a right angle away from your view on the tree. And then you're going to stand over here, and you're going to look back at the tree. And you'll have like a rock over here that you can recognize, and the tree on the opposite side, and you can measure this angle.
Oh.
There's a little device. Well, you could use a protractor, I guess. You can hold it up and kind of eye it. I don't know. But they do have devices. You see those guys surveying the roads with those little telescopes?
No. Yeah.
You've never seen
so.
that? They have the little telescopes and they hold that stick that's black, white, black, white.
Oh.
And they're measuring the elevations and angle turns and things like that. That would make this an easy way to calculate it. So the things you can measure is how far away you walked and the angle of change from the tree and where you were standing originally. So let's say you walked away 100 feet. And let's say that theta that you measured was 78 degrees. You should be able to find the distance across the lake. And this is what a lot of trigonometry is used for, surveying, finding distances that you normally cannot measure. Yeah, give them some warm milk too. You can take a really good nap. So what you have to figure out is what function do you need to use. So you concentrate on the angle that you're measuring, and you just name the other two sides that you're given, or the one you're looking for and the one you know. So you look at this angle. What is this side called? The D side. But what's it called according to this angle? It's opposite. What's the 100 called according to this angle? Adjacent. So the function you want has an opposite and adjacent in it, which is tangent. So you go tangent of this angle, which is 78 degrees, is equal to opposite, which is D, over adjacent, which is 100. So it gives you a nice little equation, one unknown. How do you solve for the one unknown?
Tangent 78 divided by 100.
What? No. How do you get D by itself? You multiply by 100.
I'm sorry, multiply by 100.
Well, that's a big difference. I'm going to give you 100 times your pay or 100th of your pay.
Oh, God.
I think I'll give you 100th of your pay.
No.
So D equals 100 times tangent of 78 degrees. Now, be careful. Your calculator has to be in degree mode for this thing to work out. So you just type it in, 100 tangent 78, it equals. You get an answer. Oh, approximate answer.
Oh, mine's radians.
470.
Wait, how do you put it in?
Literally, just type in 100, hit the tangent button, 78.
No,
I got 470.
I got
470.
470 times 463
Blah, 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 blah. 470. It's approximately 470 what?
Degrees.
No. It is definitely not degrees. Feet. You're looking for the distance across the lake. Now be careful, these word problems, you have to know what you're really solving for. If you put a degree there, it's wrong. I'm just going to mark it wrong because you're out in space.
Degrees.
Huh?
I got negatives, so how do you change it?
Hit mode. Are you in the big calculator?
Yeah.
Yeah, hit mode. There should be a radian. Just move it over, hit enter, and then go back.
So you're gonna take off the
No,
You better, yeah, I'm going to take off a point if you don't. But if you say 470, I have no idea what you're talking about. Apples? Bananas?
Oranges.
Oranges?
Pineapple.
Pineapples?
Cantaloupe.
Imagine having 470.
Star fruit.
Cantaloupe.
What else could we do? We could do these type problems. A little drawing here.
I lost one.
This is
That's a football.
this is Egyptian.
That's a football.
This is an eye. So if this is your eye and you're looking straight ahead, parallel to the ground,
Shouldn't you be drawing?
whatever. This is called line of sight. You're looking straight ahead. You're not looking down. You're not looking up. You're looking parallel to the ground. It's called line of sight. So if there is an airplane up here, or a bird, or anything that's up in the sky, it's a rocket airplane. You're going to look up at Now if you look up at it, it's going to change the angle away from the horizontal, and this angle here,
We're solving.
I'm trying to think of what I should call it. Let's just call it theta. This angle is called the angle of elevation or inclination. One of the two, elevation or inclination, depending on which way you want to go with it. If you are looking down at the ground at some ant, I don't know, it's got legs. Some ant. Evil ant. And you're looking down at this ant, and let's call this angle alpha. This is an angle
Isn't it?
of depression.
Very funny.
It's the angle of depression. Now, there is a neat relationship between these two things. For instance, if you're standing at the top of a building, up here, little stick figure going on.
Don't jump.
Definitely don't jump. We could talk about how fast it'll take you to get down there if you really want to get
Don't
into that
jump.
problem. Yeah.
More to live more than this.
And there's a car down here, Jetson car.
With wheels.
Okay, and this person is looking down at the car. They have an angle of depression.
But
Where
the car
would it
has the
measure?
angle of elevation.
I know. But if you're this person, where is the angle of depression? Is it here against the building?
Yes.
No.
It's
It's a gun. You have to get that horizontal in there. So this is the angle of depression. Let's call it, what do I call it up there?
the
Alpha.
theta.
Alpha. Alpha's the depression one. Now, if you're a person in the car looking back up at the person at the top of the building, this angle is the angle of elevation, and this would be theta. But what's true about alpha and theta?
They are, I forget the term, but they're equal.
They're equal to each
Yeah,
other.
right.
It's called alternate interior angles because these two lines, top and bottom, are parallel to each other, and this is a transversal. So the angle of depression from the top is equal to the angle of elevation from the other perspective. So anytime you want to change an angle of depression into an angle of elevation, I highly suggest that you do. Why? Because most people take the angle of depression and put it against the building. And that makes everything, well, wrong. It's easier for angles of elevation because you already have a line there and you're coming up. So anytime you have someone looking down, change it around to the other person looking up. It'll save you a lot of headache. For instance, how much time do we have?
It's quiz time.
No, I don't have a quiz.
You don't have a quiz?
You didn't have homework,
Yes.
which means I get to teach more. What happens to the yes? You know, yes.
She said yes.
Teach more.
Yes, ma'am.
Yes. Okay. So let's say we're in an airplane.
Why can't we just do it that way?
And he's flying straight ahead.
Okay.
So he's not changing his altitude. The only thing this pilot knows is here's some water. He's over the ocean. And he knows the altitude he's flying at is 2,500 feet. So only his what's that called?
Alternate in
No, the height of a plane. There's a device that measures the height of a plane.
altitude.
Altimeter?
Altitude.
Altimeter? Yeah, something like that. So only that thing is working, but his speedometer is not.
That's awful.
That's awful. His speedometer broken. He wants to know how fast he's going. So over here in the distance is a deserted island. And we have a tree. Now we're in the tropics, so it's a nice little palm tree.
Nice.
Whatever.
What is it? Kind of some coconuts on it.
I am not putting any coconuts on it. So, to find out how fast he's going to measure his angle of depression and then separate those up. He's going to do two measurements. He's going to do one right here, then he's going to wait a little bit of time and do one more. What's going to happen to the angle is it's going to get bigger.
Bigger.
Bigger. It's going to start off here. By the time you're over here, it's going to be bigger. So we're going to do two measurements. So
So while
The first one, let's let it be 20 degrees. The second one, let's let it be 90, no, it can't be 90, 85 degrees. And these are 10 seconds apart. A 10-second span happened. So as he's flying along, he measures the first one as 20 degrees, angle of depression down to that island. The second time he measures it, he's closer to the tree, so the angle is going to be bigger.
Much deeper.
He measured it.
They
If you
like
have a device, you can measure angles.
What are they called?
I'd rather him
Line?
just follow.
Well, a protractor would be fine.
No, like they have like this
He stuck
this
the
thing.
protractor on
Like
one wall, I was
the
like,
military uses it.
Oh, I have no idea.
It's like it starts with an A.
Oh,
Let's see what we got.
I think it's like. I don't know.
I don't know.
Close to your face. Wise guys do
So,
that.
what I want to do is,
Shh.
I want to find out how fast this plane is going. So I know, pretty much where I'm going to end up. I want to know when I can land, if I have enough fuel and all that other fun stuff. So we're going to set up two triangles. Triangle number one is going to look like this. Here's your plane, here's the tree, and you're flying this way, and your altitude is here. You have to draw it this way, otherwise things get really bad. So if you draw it this way, your habit is to put that angle against the altitude, and you can't do that. Your angle has to go across the horizontal. So this is the distance. Well, that's not the distance we're interested in, but this is angle theta, angle of depression. This side I know is 2,500 feet. What side do I want to find? The top one. So let's call this one x for now.
I thought he wanted to know how fast he was going.
He does.
But I'm going to figure it out. Watch.
I'm not
So,
following.
the first theta is equal to 20. So what function is going to associate these three pieces? That's a right angle, by the way.
Tangent.
Tangent again. So you're going to go tangent of this angle, which is 20, is equal to 2,500 over x.
Why are you doing tangent again?
Because when we're talking about this angle of depression, this side is opposite, this side is adjacent, this side is hypotenuse. I don't know anything about the hypotenuse. If you don't have an hypotenuse, it's definitely tangent. If you have a hypotenuse, it's either sine or cosine. How do you solve for x?
2,500 divided by tangent.
Well, you can treat this as a proportion and take these two pieces and flip them. So you get x on this side is equal to 2,500 divided by tangent of 20.
68.
If you don't see that trick, multiply both sides by x, and then you divide by the tangent. So this is approximately
68.
68.
69.
0.69.
Oh dear Lord, 0.7 feet. Fine. Now, we change it to the other angle, which is
85.
85 degrees. So when it's 85 degrees, I'm not going to choose x because it's not x anymore, so I'll draw my picture over again. It'll probably be more like this. This side is still 2,500. This side, we're going to call it now y. It's different. And the angle here is 85 degrees. The setup is the same. Tangent of 85 degrees is equal to 2,500 over y. The answer for y is going to look really similar. 2,500 over tangent of 85. And y is approximately
219.
219. That's it? And this would be feet. So how do you find out how fast he's going?
You divide them.
Subtract them first. That tells you
The distance between them.
how far you've gone. Displacement, if you want to call it that. Then what's their subtraction? So x minus y? What's that equal?
6,649.
6649? 0.7?
Yep.
And the time that they traveled was
10 seconds.
10 seconds. Oh, 10 seconds. So what does that tell me? Well, it's feet in the top, right? Seconds in the bottom, so this turns into 665 feet per second.
How did you get, wait,
that
All
way?
10 seconds.
10 seconds. I took my measurements 10 seconds apart.
Oh, okay.
So therefore, that's how long time elapsed, and that's how far I've traveled. You have two people doing this. You have one person measuring the angles, the other one keeping track of time. I don't think you could do it at the same time. So how do you change 665 feet per second into something more viable? In other words, understandable.
Miles.
I need to change it to miles per hour.
So you do.
There is a shortcut. Which one's bigger, the miles version, feet to miles, or seconds to, well,
Seconds
yeah,
to
seconds to hours? How many seconds in an hour?
60.
60 squared.
Yeah.
3,600. And feet per mile? 5280.
Yeah,
5280.
665.
So to get rid of the feet, it would go in the bottom. So that would be 5280 in the bottom, and the seconds would go in the top. That fraction actually turns out to be 15 over 22.
How do you
It's 3,600 over 5280
Can you
reduced.
know?
Reduced. Do you want me to write it out?
Yeah.
It would be 665 feet per, what is it, second, right?
Centimeters. Yeah.
And you're going to multiply that by, change the feet, and you want to change it into miles. There are 5280 feet per mile. And over here, you want to get rid of the seconds, so that has to go up top, and there's 3,600 seconds per hour. There's 60 seconds in a minute, and 60 minutes in an hour, so 60 60s. And 3,600 divided by 5280 reduces to 15 over 22. So what's 665 times 15 divided by 22?
Times what?
You are
665.
Yeah, you were just like going like.
665 times 15 divided by 22.
I don't know.
You can do this calculation too if you want.
Alright.
Comes out the same.
665.
What is it?
453.4.
And this is miles per hour. Going along at a good clip. Either one works. The 15 over 22 is just a neat little shortcut to go from feet per second into miles per hour. Now if you want to go backwards, miles per hour to feet per second, you take that fraction and flip it. It becomes kind of easy. So this is a way an airplane pilot can figure out how fast he's going if he doesn't have a speedometer.